Hello everyone, welcome to this lecture 45 of the NPTEL course on Riemannian geometry. So last time I introduced this notion of a Jacobi field, so let me remind you of what that was. So we fix a geodesic gamma from A to B to M, and we assume that the initial point is P and the final point is Q. Then a smooth vector field along gamma is called a Jacobi field if it satisfies this so called Jacobi equation, right. So it is a second order linear ODE. So then by the standard theory of linear ODEs, we get the following existence and uniqueness result, that if you take any if you fix a time t naught in this interval, it could be either a or b or any time in between, and if you fix two vectors v and w in the tangent space to M at gamma of t naught, then there exists a unique Jacobi field. So this J of gamma denotes the set of Jacobi fields along gamma. So there exists a unique J in J of gamma such that the value of J at t naught is V and the derivative at t naught is W. So of course all these derivatives are covariant derivatives along gamma, right. So they are covariant derivatives with respect to the velocity gamma dot. Okay, and then at the end of the lecture I proved this very basic and fundamental result, that a vector field is a Jacobi field if and only if for all w in the tangent space to the path space. So that means any admissible vector field w that vanishes at A and B, the index form applied to j comma w is 0. So I should say that suppose you have any admissible vector field j such that it satisfies this condition, that any w in the tangent space pairs to 0 via the index form, then j is not only smooth but it also solves the Jacobi equation, right. So that is what the statement was. Okay, so in this lecture I want to sort of continue studying these Jacobi fields. So let me first maybe give you a couple of examples. Okay, so let us first talk about Jacobi fields. On the Euclidean space with the usual Euclidean metric, right. So in this case the geodesic is basically just a straight line. So this is some straight line AT plus B for some vectors AB in Rn. On the other hand, what is the Jacobi equation? Because we are working in Rn, the curvature tensor is identically 0, right. So the Jacobi equation reduces to j double prime is 0, but in Euclidean space the covariant derivative is the ordinary derivative. So this implies that j of t itself is given by some ut plus or some lambda t plus mu, right. Where lambda mu are in R. So in particular if you look at the Jacobi field which vanishes at some initial point, so in particular say our initial point P is the origin, okay, and suppose I am looking at the Jacobi field that vanishes at that point, right. Then your j of t is simply given by some lambda times t. So the picture is the following. So your geodesic is a straight line passing through 0. The Jacobi field vanishes at this point, and at all other points it basically points in the direction of lambda, but the norm will keep changing as t changes, right. So the picture is the following: you have something like this, and similarly in the opposite direction, so on, right. So in Rn the Jacobi fields have this simple expression. In the next lecture we are actually going to see that if one uses normal coordinates at centered at some point p, then the Jacobi fields that vanish at p along these radial geodesics at p actually look exactly like this picture in normal coordinates, right. So that is something that we will see next time. So in a sense the local picture of all Jacobi fields on any abstract Riemannian manifold is basically just given by this picture, okay. Alright, so the second sort of class of examples, so these are very general Jacobi fields that one can construct on any along any geodesic. So these are the so called tangential Jacobi fields, okay. So again let us say I am given a geodesic gamma, okay, and let us say I have a point t naught. T naught could be any point. We let j naught of t be simply gamma dot of t, and j1 of t be simply t minus t naught gamma dot of t, okay. So then one can easily check, and this is a nice exercise. I mean it's a simple exercise, but you should try that j naught and j1 are indeed Jacobi fields along gamma, okay. And in fact they satisfy the following initial conditions. Okay, so if you take j naught of t naught, that is obviously the velocity vector at t naught. Also if you differentiate j naught, then that is 0, because I mean that is the geodesic equation, right. So so j naught prime at t naught will also be 0. On the other hand, if you plug in j1 of t naught, then that is obviously 0, and j1 prime at t naught. So you can differentiate and see that this is precisely gamma dot of t naught, okay. So these two Jacobi fields can be constructed along any geodesic, okay. Alright, so here's some notation. Let me maybe make a definition first. So given a curve, not necessarily a geodesic, a vector field x along it, a smooth vector field let us say, is called tangential if at each point x is given by a scalar multiple of the velocity vector, okay, and it is called normal if at each point x of t is perpendicular to the velocity vector, okay. So the notation is the following. So this is the set of tangential vector fields this is the set of normal vector fields okay, and then one can also intersect this, one can look at the tangential Jacobi fields and the tangential and the normal Jacobi fields. So there the notation is as follows. Okay. So we have the following elementary proposition which characterizes all the normal Jacobi fields. Okay. So let gamma be a geodesic with, let us say, 0 in I, okay, or some T naught in I, and let J be a Jacobi field. Then we have the following. The first result is a very basic calculation which will be useful for the rest of the course, that if you take the inner product of the Jacobi vector field with the velocity vector field, then this is an affine linear function. Okay, or equivalently, this just means that if you take two derivatives of f, that is 0. Okay. The second point is that J is a normal Jacobi field if and only if J of 0 and J prime of 0 are perpendicular to gamma dot at 0. Okay. And if and only if J of 0 is perpendicular to gamma of 0 and there exists another T naught not equal to 0 such that J of T naught is also perpendicular to the velocity vector at T naught. Okay. So both these criteria are equivalent to J being a normal Jacobi field. And as a consequence of this, if you take the set of normal Jacobi fields, this is a linear subspace of J of gamma to n minus 2. Okay. All right. So here's the proof. So the second and the third parts follow easily from the first part. So let's calculate what the second derivative of f is. Okay. So what is f prime? Well, by the product rule you differentiate first J and then differentiate gamma dot. The derivative of gamma dot is 0 because gamma is a geodesic. So this will just be J prime times gamma dot. Okay. Similarly, what is f double prime? Again the derivative will only hit J, so it will be J double prime times gamma dot. But what is J double prime? By the Jacobi equation, J double prime is minus R J gamma dot, right. So f double prime is the inner product of, or rather minus the inner product of R J gamma dot, which is just the negative of the Riemann curvature tensor applied to these 4 vectors. But now in the final 2 entries this is skew symmetric. So if the entries are the same, this has to be 0. Okay. So f double prime is 0 and that complete so that means f has to be an affine linear function. For the second part, so by the first part f of t is some at plus b, okay, right. So so then J is a normal vector field if and only if both A B are 0, right. But what is I mean what is A? A is simply f of 0 and sorry A is simply f prime at 0 and B is simply f of 0, okay. But then by the definition of f and the and our calculation for the derivative of f, so the derivative of f was given by this. This is equivalent to the statement that j prime of 0 is perpendicular to gamma dot and j of 0 is perpendicular to gamma dot, okay. Then for the second equivalence, we just have this observation that an affine linear function vanishes identically if and only if it vanishes at 2 points. Okay, so that completes the proof of the second equivalence, that as long as j at 0 and j at some other t naught are orthogonal to the velocity vectors, your j has to be a normal vector field. And then for the third part, we note that by the second part this is orthogonal if and only if j of 0 and j prime of 0 are perpendicular to the velocity vector. So that means for j of 0 there are n minus 1 dimensions worth of choices. Since j of 0 has to belong to the orthogonal complement of the velocity vector in the tangent space, but the same is true for j prime of 0, right. So that means you have n minus 1 plus n minus 1 dimension worth of choices. So this means that the dimension of the space of normal Jacobi fields is 2n minus 2. Alright, so that completes the proof of this. Okay, so the final thing I want to do in this lecture is to give a characterization of Jacobi fields. How do you produce Jacobi fields? So the idea is that Jacobi fields arise geometrically as variation vector fields of variations through geodesics. So maybe I'll start on the right. So as I was saying in the final part of this lecture, I want to give a natural sort of geometric construction of Jacobi fields, and they arise by looking at these things called as variations of geodesics. So variations through geodesics. Okay, so here's a definition. So let gamma st be an admissible variation. We say that it is a variation through geodesics if for all s gamma s of t, so you are looking at these horizontal curves, it is a geodesic. Okay, so each of the horizontal curves in that variation is a geodesic. So then the basic proposition is the following, that let gamma be a geodesic and capital gamma a variation through geodesics. Or rather, sorry, let me. So then the characterization of Jacobi fields is the following. So then J is a Jacobi field along gamma if and only if there exists a variation through geodesics such that J is actually the variation vector field. So such that J of t is the variation vector field of gamma. Okay, so let's prove this. So the easier direction is the backward direction. Suppose you have a variation and you look at the variation vector field of this. I want to show that it's a geodesic. So suppose J of t is this, and little gamma s of t is a geodesic for all s, right. Then my claim is that J is actually a Jacobi field. So I have to verify that it satisfies the Jacobi equation. So as usual my notation is going to be S is going to be the sort of transverse derivatives and T is going to be the velocity vectors of the horizontal curves. Okay. So then if you look at dt of t, well that's going to be 0 because it's a variation through geodesics. Okay. Why? Because gamma s is a geodesic. Okay, so now you differentiate in S, okay, but then by the definition of curvature and the fact that that del by del s and del by del t commute, we have that this is going to be the same as dt ds of t plus a curvature term. Okay. But then by the symmetry lemma, so if you look at this, by the symmetry lemma this is the same as this, right. So this is dt of s plus r of s dt. So now if you plug in s equals 0, this is precisely j double prime plus r of j gamma dot gamma dot. So this implies that j is a Jacobi field. Okay, so that is the easier direction. Now for the converse. Okay, so here we are assuming now that J is a Jacobi field and our job is to produce this this variation through geodesics whose variation vector field is J, right. So the idea is the following: you take this point P and Q, let us say this is gamma. So let V be equal to J of 0 and W be equal to J prime at 0. So what we do is the following, we take a little sigma. So so let us say our V is given by this, let us say this is V, maybe I will draw a better picture, right. Yeah, so let us say this is V, then the idea is that you take a little curve here with that as the velocity vector, okay. So let sigma such that sigma of 0 is P and sigma prime at 0 is V, okay. Alright, so now what we do is the following, so let V of S and W of S be the parallel transports of the vectors V and W along this new curve sigma of S, okay, and we consider the following. Consider gamma of St as simply the exponential at sigma of S. So again going back to the picture, what you do is the following, so you are at this point sigma of S, you have these vectors V of S and possibly W of S. You basically take the exponential map of some linear combination of V of S and W of S. So that is going to be our curve little gamma S of t, okay. So more formally you take the exponential map at sigma of S of V of S plus of t times V of S plus S times W of S, okay. Then clearly for each S, gamma of S is, if you fix an S, gamma S is some exponential map, so it is some radial geodesic, so it is clearly a geodesic, okay. So let us I mean my claim is that J is in fact the variation vector field of this variation, okay. So what is the proof? So let x be that variation vector field, so let x of t be equal to this. Our job is to prove that x and j are actually the same vector fields, okay. So firstly by the first part, x is clearly a Jacobi field because it is the variation vector field of a variation through geodesics. Then in the first part we saw that means that x has to be a Jacobi field. So let us try to compute, goal will be to compute x of 0 and x prime of 0, okay. So what is x of 0? Well x of 0 is precisely del by del s equal to 0 of gamma of s comma 0, right, because you are only computing the derivative in the s direction, so you can put t equal to 0, okay. But what is this? This is del by del s equal to 0. When you put t equal to 0, that is just going to be exponential of sigma of s of 0, but exponential map takes 0 to sigma of s. So this is just going to be the velocity vector of sigma at 0, which is v, okay. So capital X of 0 is v, alright. What is the derivative x prime at 0? Well that is going to be del t del s of gamma at 0 0, okay. So then by the symmetry lemma you can again switch these two, right. So that is going to be ds at s equals 0 of del t gamma at t equal to 0, Okay, but what is the derivative of this? So the derivative of this at t equal to 0, this is basically a geodesic in the direction of v of s plus s w of s. So the derivative, the velocity vector of that geodesic at t equals 0 is just going to be precisely v of s plus s w of s. Okay. But now the s derivative is just going to be v prime at 0 plus you differentiate s, you get w of 0 plus you put 0 times w prime at 0. Okay. But this is obviously 0, but also v is a parallel vector field, right. So this is also 0. So this is just going to be w at 0, but w at 0 is just little w. So the upshot is that X is a Jacobi field with these two initial conditions, but J was also a Jacobi field with these two initial conditions. So then by the uniqueness of Jacobi fields, X and J have to be one and the same. Okay, so that completes the proof of this proposition. Okay, so maybe that's it for this lecture. In the next lecture, we'll continue our study of Jacobi fields, and we'll derive some, in the next couple of lectures we'll derive some beautiful consequences of the fact that we can actually calculate what Jacobi fields look like. Okay, so anyway, that's it for this lecture. Thank you for your attention, and I'll see you in the next lecture. Thanks.